Hello everyone and welcome to this lecture on DC drive 1. In last lecture, we were discussing about the speed control of induction motor and synchronous motor using AC drives. Today, we will discuss about speed control of DC motor using single phase and 3-phase DC drives. So, let us start with DC drive. Among the electrical motor, the DC motor are very versatile in that they provide a smooth speed control over a wide range. They have been very widely used in industry as variable speed drive. As we know, the speed of DC motor is equal to V minus IaRa upon K phi, where V is the terminal voltage, Ia is armature current, Ra is armature resistance and phi is the flux. So, hence speed of DC motor can be varied by changing the terminal voltage of the armature, which is known as armature voltage control method, and inserting an external resistance in armature resistance Ra, which is known as armature resistance control method. The another method is by varying flux per pole, that is known as field flux control. Their speed below base speed can be controlled by armature voltage control. Speeds above base speed are obtained by field flux control. As speed control methods for DC motor are simpler and less expensive than those for AC motors, DC motor are preferred where wide speed control range is required. The introduction of thyristor and the development of the power converter using thyristors has made the speed control of electrical motor more easier and more straightforward. The main disadvantage of this motor is the presence of a mechanical commutator, which limit the maximum power rating and the speed. Now, we will deal with DC types of DC motor drives. So, first is non-generative DC drives. In this drive rotates only in one direction and hence also called as single quadrant drive. This drive does not have any inherent braking capability. The motor is terminated by removing the supply. Such type of drive is used in a place where high friction load or strong natural brake is required. The another one is regenerative DC drive. It is a 4-quadrant drive and it controls the speed, direction and the torque of a motor. Under the braking condition, the drive converts mechanical energy and the load into electrical energy, which is returned to the power source. There are different application of DC motor drives such as rolling mills, paper mills, mine winders, hoist, machine tool, traction, printing presses and textile mills. Now, we will study controlled rectifier fed DC drive. Control rectifier fed DC drive are used to get variable DC voltage from an AC source of fixed voltage. Phase controlled converter provide an adjustable DC output voltage from a fixed AC input voltage. DC chopper also provide DC output voltage from a fixed DC input voltage. The use of a phase control rectifier and DC chopper from the speed control of DC motor have modernized the industrial control system. The control rectifier fed DC drive are also known as static Ward Leonard drives. There are several types of converter which can be used for feeding DC motor. The DC motor used in conjunction with power electronics converter are DC separately excited motor or DC series motor. Depending upon the type of AC source or the method of voltage control, DC drive are classified as under. The first one is single phase DC drive, the second one is 3-phase DC drive, and third one is chopper drive. These drive can be full wave or half wave or semi converter drives. A full wave drive can be supplied from a fully controlled or half controlled converter. A dual converter can be obtained by a connection of 2-quadrant converter. 1-quadrant operation is possible with the half control converter as it contains diode in several positions. Figure shows commonly used controlled rectifier fed DC drive and quadrant in which they can operate on VA and IA plane, as thyristors are capable of conducting current only in one direction. All these rectifiers are capable of providing current only in one direction. The fully controlled converter is capable of 2-quadrant operation. The rectifier shown in the figure provide control of DC voltage in either direction and therefore allow motor control in quadrant 1 and quadrant 4 respectively. They are known as fully controlled rectifier. For low power application up to around 10 kilowatt, single phase rectifier drives are generally employed. For high power application, 3-phase rectifier drives are used. So, next we will deal single phase DC drives. In single phase DC drive operating in these drives, phase control converter operating from a single phase are used to drive the motor. These are used for low and medium power application. These have inherently poor speed regulation with open loop control. This can be improved by closed loop operation. Single phase DC drive, the figure demonstrate the general circuit arrangement for the speed control of a separately excited DC motor from a single phase source. The firing angle control of the converter 1 regulates the armature voltage applied to the DC motor armature. Thus, the variation of the delayed angle alpha 1 of converter 1 gives speed control below the base speed. The variation of the firing angle alpha 2 of converter 2 installed in the field circuit gives speed above base speed. The low value of alpha 1 for converter 1 armature current may become discontinuous. The discontinuous armature current causes more losses in the armature and poor speed regulation. It is usual to insert an inductor in series with armature circuit to reduce the ripple in armature current and to make the armature current continuous for low values of motor speed. Depending upon type of power electronics converter used in armature circuit, single phase DC drive may be subdivided as under. The first one is single phase half wave converter drive, second one is single phase semi converter drive, third one is single phase full converter drive, and last one is single phase dual converter drive. So, first we start with single phase half wave drives. The single phase separately excited DC motor drive is supplied from a single phase half wave circuit. The conduction angle of the thyristor is very small, resulting in a very low average current. The torque developed is very small, resulting in a loss of torque at the rated RMS current. The RMS of the average current ratio is also more. The motor current is always discontinuous. The ripple frequency is equal to supply frequency. The current and voltage waveform are shown in the figure. The freewheeling diode across the load improves the performance. The speed regulation is very poor. The speed oscillation is quite high. The application of this drive is limited to low power only. Low cost and simplicity are the advantage of this drive, and this can provide only one quadrant operation. The single phase half control rectifier shown in the figure, the thyristor T1 receive gate pulse from alpha to pi, where alpha is the firing angle, and transistor T2 from alpha, pi plus alpha to 2 pi. Motor is shown by its equivalent circuit in the figure. For single phase half control rectifier, average output voltage is V naught, and V naught is equal to Vm upon 2 pi 1 plus cos alpha, where alpha lies between 0 and pi. Vm is maximum value of source voltage and alpha is firing angle. So, as we change the value of firing angle alpha, we can control the output voltage of the rectifier, and hence we can control the supply voltage to the motor, and as supply given to the motor is varied, so speed of the motor can be varied accordingly. The motor terminal voltage and current waveform for the discontinuous and continuous conduction mode are shown in the figure. In discontinuous conduction mode, when T1 is fired at alpha, motor get connected to the source through T1 and D1, and VA is equal to Vs. The armature current flows and D2 get forward biased at angle pi. As a result, armature current freewheels through the path formed by D1 and D2 diodes, and the motor terminal voltage is 0. Conduction of D2 reverse bias T1 and turns it off. Armature current drops to 0 to beta and stays 0 until T2 is fired at pi plus alpha. A cycle of motor terminal voltage consists of 3 intervals. First interval is duty interval, which is from alpha to pi when motor is connected to the source and VA is equal to Vs. Second interval is 0 current interval, which is from beta to pi plus alpha when IA is equal to 0 and VA is equal to back EMF of motor. And third interval is freewheeling interval, that is between pi to beta. Speed torque curves are shown in the figure. A single phase half wave control rectifier is cheaper and gives high power factor compared to single phase fully controlled rectifier, but then it only provides control in quadrant 1 as is shown in the figure. Now, next topic is single phase semi converter drives. A separately excited DC motor fed through two single phase semi converter, one from armature circuit and another from field circuit as shown in the figure. Both converter 1 and 2 are connected to same source, that is single phase source. This converter also offer one quadrant drive and it is used up to 15 kilowatt DC drive. A single phase semiconductor is also called as single phase half control bridge converter. For single phase semiconductor, average output is V naught, and V naught is equal to Vm upon pi 1 plus cos alpha 1, where alpha 1 lies between 0 to pi. The waveform of the current and voltage are shown in the figure on the assumption of ripple free armature current. For field circuit, Vf is equal to Vm upon pi 1 plus cos alpha 2, where alpha 2 lies between 0 to pi, where Vf is field voltage. Next is single phase full wave drive. The single phase separately excited DC motor drive is supplied by a full wave converter. A full wave drive using a fully controlled converter is shown in the figure. Having thyristor in all positions, the firing of the thyristor allow negative average voltages, making the power flow from load to back to supply. The motor can be braked effectively using regenerative braking. The motor is shown by its equivalent circuit on the load side. When field control is required, field is fed from controlled rectifier, otherwise from an uncontrolled rectifier. The AC input voltage is defined by Vs is equal to Vm sin omega t. In the cycle of source voltage, thyristor T1 and T3 are given gate signal from alpha to pi, and thyristor T2 and T4 are given gate signal from pi plus alpha 2 to pi. When armature current does not flow continuously, the motor is set to operate in discontinuous conduction. When current flows continuously, the conduction is said to be continuous. The drive under consideration mainly operate in discontinuous conduction. Discontinuous conduction has several modes of operation. The motor terminal voltage and current waveform for the discontinuous conduction and continuous conduction mode are shown in the figure. In a single phase fully controlled rectifier control of DC motor, the terminal voltage Va, the drive operates in two intervals. First one is duty interval, when omega t lies between alpha and beta, where motor is connected to the source, that is Va is equal to Vs. Zero current interval, when omega t is between beta and pi plus alpha, where Ia is equal to 0 and Va is equal to E. In this mode, the current start flowing with the turn on of thyristor T1 and T3 at omega t is equal to alpha. Motor get connected to the source and its terminal voltage equal to Vs. The current which flows against both E and the source voltage after omega t is equal to pi falls to 0 at beta. Due to the absence of the current, thyristor T1 and T3 turn off. Motor terminal voltage is now equal to its induced voltage E. When thyristor T2 and T4 are fired at pi plus alpha, next cycle of motor terminal voltage Va starts. In continuous mode, a positive current flows through the motor and thyristor T1 and T4 are in conduction just before alpha. Application of gate pulse turns on forward bias thyristor T1 and T3 at alpha. Conduction of T1 and T3 reverse biases T2 and T4 and turns them off. A cycle of Va is completed when T2 and T4 are turned on at pi plus alpha, causing turn off of T1 and T3. For single phase full wave converter, the average voltage V naught is given as 2 Vm upon pi cos alpha, where alpha lies between 0 to 2 pi. The boundary between continuous and discontinuous conduction is shown by dotted line in the figure. For torque less than rated, a low power drive mainly operated in discontinuous conduction. In continuous conduction, the speed torque characteristics are parallel straight line whose slopes depend on armature circuit resistance R A. Effect of discontinuous conduction is to make speed regulation poor. Its use is limited to about 15 kilowatt only. For regenerative braking of the motor, the power must flow from motor to AC source, and this is feasible only if motor counter EMF is reversed, because then EAIA would be negative. Note the direction of the current cannot be reversed as SCR unidirectional device. So, for regenerative braking, the polarity of EA must be reversed, which is possible by reversing the direction of the motor field current by making delay angle of full converter to more than 90 degree, in order that current in field winding can be reversed. The field winding must be energized through single phase full converter. The motor can be braked effectively using regenerative braking. This can be made possible at constant current, as the load current flows both during positive and negative half cycles. The average value of the current is more than that in half wave drive. The torque capability increases for a given armature heating. The speed oscillation is less. The speed regulation improved because of increased conduction of current in the load. Now, next topic is single phase dual converter drive. A single phase dual converter obtained by connecting two full converter in anti-parallel as shown in the figure, feeding a separately excited DC motor. Its use is limited to about 15 kilowatt DC drive. It offers 4 quadrant operation. For working in first quadrant and fourth quadrant, converter 1 is in operation. For operation in second and third quadrant, converter 2 is energized. 4 quadrant operation demand that field winding of the motor is energized from single phase or 3 phase full converter. For converter 1 in operation, V1 is equal to T 2 Vm upon pi cos alpha 1, and for converter 2 in operation, V is equal to 2 Vm upon pi cos alpha 2, where both alpha 1 and alpha 2 lies between 0 and pi. For converter 1 with alpha 1 less than 90 degree operates the motor in forward motoring mode, that is first quadrant. For quadrant 1 with alpha 1 greater than 90 degree and with field excitation reversed operates the motor in forward regenerating braking mode, which is in fourth quadrant. Now, if the converter 2 with alpha 2 less than 90 degree operates the motor in reverse motoring mode, that is third quadrant. Quadrant 2 with alpha 2 greater than 90 degree and with field excitation reverse operate the motor in reverse regenerative braking mode, that is quadrant 2. Now, next topic is 3 phase DC drive. DC drive motor drives Large DC motor drives are always fed through 3-phase converter for their speed control. A 3-phase control converter feeds power to the armature circuit for obtaining speed below base speed. Another 3-phase control converter is inserted in field circuit for getting speed above the base speed. The output frequency of 3-phase converter is higher than those of single phase converter. Therefore, for reducing the armature current ripple, the inductor required in 3-phase DC drive is of lower value than that in single phase DC drive. As armature current is mostly continuous, the motor performance in 3-phase DC drive is superior to those in single phase DC drives. The 3-phase DC drives may be subdivided as under 3-phase half wave converter drive, 3-phase semi converter drive, 3-phase full converter drives, and last one is 3-phase dual converter drive. The 3-phase converter can be used to give 3 or 6 pulse in the output. The output voltage has less ripple when the number of pulses increases. Therefore, 3-phase converter produce an output voltage within reduced harmonic content. The firing requirement and therefore less in the output circuit. The speed regulation of the drive improves and the speed oscillation of the motor are small. Now, first is 3-phase half wave drive. Single phase drives discussed in previous session are employed for low and medium power. When the power of drive is very large, the 3-phase converter is preferred for supplying the load. This converter offers one quadrant operation and may be used up to about 40 kilowatt motor ratings. The drive performance can be improved by connecting a free wheel diode across the supply. The connections are shown in the figure. The drive is preferred to the above if not regenerating is the free wheeling diode improves the line power factor beside providing the beneficial effect of decreasing the ratio of peak to average and RMS to average current of the load by providing a kind of smoothing of the load voltage. The 3-phase half wave converter is not normally used in industrial application because the supply current contain DC component. The figure shows waveform of output voltage and armature current. The armature heating is therefore less. The amount of inductance required in the load for filtering the harmonics is less. For rectifier circuit shown in the figure under continuous conduction, the armature voltage is given by 3 Vm upon 2 pi 1 plus cos alpha. As the voltage across motor is dependent on firing angle. So, by varying the firing angle, we can change the speed of the motor as the voltage across the motor is varied. So, the next topic is 3-phase semi converter feeding separately excited DC motor. Large kilowatt motor are fed from 3-phase supply through 3-phase converter. In a 3-phase semi converter, the ripple frequency of the motor terminal voltage is higher than that in the single phase converter. As a result, the filtering requirement for smoothing out the motor current are less and the current is most continuous. Semi and full converter are most common in use. A dual converter is employed for reversible drive with a power rating up to several megawatt. The three-phase semi-converter feeding separately excited DC motor is shown in the figure. The figure shows the phase voltage waveform applied to the converter. The convenient references for the thyristor firing angles are omega T1, omega T2, omega T3 and so on, which are spaced 120 degree apart. The three thyristor fire in sequence with a time spacing of 120 degree as shown in the figure. After thyristor TH1 fires, diode D2 and D3 conducts depend upon the voltage is more positive of VAB and VAC. For the value of alpha chosen, it may be seen in the figure that diode D2 conducts up to 90 degree, beyond which D3 conducts till thyristor TH2 fires. Then D3 and D1 conduct till thyristor TH3 fires, followed by D1, D2 conducting in sequence. This process then repeats, resulting in voltage waveform of VA as shown in the figure. For this value of alpha, 3 freewheeling diode is not called upon to conduct the armature current. The armature current IA and line current IA are shown in the figure respectively. The fundamental IA1 of the line current lags by a small angle phi 1, resulting in less than unity power factor. So, we stop here for today's lecture and we will continue in the next lecture. In next lecture, we will discuss remaining part of the DC drive, which includes 3-phase fully controlled DC drive and chopper drive. So, thank you everyone and keep learning.